Yeah, well, let me get started. So welcome, everyone. So I'm Dan Boschen. I'm happy to be here. This is actually my first time at the GNU Radio Conference. Lots to learn about that. But my background, I'm primarily a hardware engineer. So from a hardware point of view, most of my career I spent in wireless comm and designing radios. Got to touch everything from the antenna to the modem and the bilayer aspects of it, all the way up to 60 gigahertz, transceivers up to 60 gigahertz. And I'm now currently working at Microchip in Beverly on atomic clocks. So it's a little different. Lots of control loops in the atomic clocks and the common theme between them. So there's lots of signal processing opportunities, and that's what I really love is signal processing. But the common theme was always SNR, optimizing signal noise ratio. How do you just all the different types of noises and how do you deal with them? And so I'd be the one to ask, like, what's the optimum control loop or tracking bandwidth for a carrier recovery loop, for example, or what's the noise figure of a FIR filter? Put it that way in terms of working on both the analog and digital side, so more of a system, if you want to call it that, perspective on these things. So today we're going to talk about fast track to designing FIR filters with Python. So the Python part, it's a bonus. So you don't even have to know or care about Python to get the most out of this workshop, because we'll do a deep dive in FIR filters and common design practices for those. And what you're going to see with the Python will apply to MATLAB, Octave, as well as Python. So if you loaded the material to follow along, what we're going to do is the first part of this, or the bulk of it, will be about the FIR filters and design approaches, and then we'll fire up Python, and you can follow along with me if you want, or just see what we do with that. So an FIR filter, so this is showing you the basic structure, what it is. So just to get everyone on board, those z to the minus ones are a unit sample delay. So you're seeing a data path with multipliers at delayed moments and an accumulator at the bottom denoted by those additions. So it's a delay, add, and multiply. So it's a pretty amazing what you can do in DSP with just those three elements, delay, add, and multiply, in exotic ways. And so we're talking about, with FIR filters, what that is, Finite Impulse Response filter. It's a subset of all digital filters that we could do. There's also IIR, Infinite Impulse Response, and then even within FIR, we're doing the subset that is linear phase FIR filters. We'll talk a little bit about what that means, but linear phase FIR filters, that's what we're going to talk about today, and that will carry you through a lot of the filters you need to design. So if you want to get good at digital filters, this is a great starting point, and it's also what I can tell you about in 2 hours. So this is showing the idea of the impulse, so the coefficients of the filter themselves, and that's what you see, the little C's getting multiplied at each delay leg. That is what is called the impulse response of the filter. So you have on the left there, I show an impulse, and it's going into the filter. So at the first moment in time, the impulse is on the first tap, and C0 gets multiplied by it and goes to the output. So you are seeing C0 at the output. And as we move forward in time, after each tick of the clock, that's what the z to the minus 1 block means. The input is moving to the output. It's a register, a synchronous register. And so you're seeing it create the impulse response at the output of the filter. And then the output is the convolution of the input. So I'm going to do some basic, get everyone on board with the core DSP stuff that you need to know for filters, get into the design. So the output, that output ends up being the convolution of the input with the coefficients of the filter. So what you're seeing is the secret behind convolution here. Each one of those, any arbitrary input can be represented as a series of weighted impulses. So that's what's so handy about having the impulse response and the things we do with it, that if we know the impulse response of a system, then in a linear system perspective, when we're working with a linear system, we can predict any output for any input, given the input is a weighted series of impulses. So every one of those impulses is going to move through and create that same impulse response. But then we're seeing a delay and accumulation of weighted impulse responses, and that's what convolution is. And it's a small group, so if you guys have any questions on any particular slide, don't hesitate. Rather than get confused, we get all the way to the end and then you forget the question. So any questions, any part of the way, got plenty of time for that. So then finally, the Fourier transform of that impulse response. So if we know the impulse response, the Fourier transform of the impulse response is the frequency response. So that's really handy, because if we could get for the impulse response, which is just the coefficients, we can get the frequency response. Or vice versa, if you have a frequency response that we want, we can get coefficients of the filter. So in one of the rookie filter design approaches is to use the FFT to just say, okay, great, I understand the FFT, the inverse FFT, then I should be able to just take the frequency response that I want, take the inverse FFT, and get the coefficients. Makes sense, right? And that is a design approach. That's one of the ones I'm going to show you. It's just one of the worst ones, and I'll show you why. So there we have the great property that this convolution in the time domain that we talked about is multiplication in the frequency domain. So that's pretty handy. So instead of doing all that convolution stuff, if we know the Fourier transform, if we can convert to the frequency domain, then we can just do a simple product in the frequency domain. So what you're seeing there is along the bottom, we see, a spectrum, right, and it's centered on 0, that's centered on DC, just so you understand my graphics. And so you're seeing a low frequency signal and a couple of high frequency signals. Is that a real waveform in time or a complex waveform in time? Let's just see if anybody knows this stuff. It's real. What? That's real, right? So if it's real in time, it's complex conjugate symmetric in frequency. We think it's real. I'm not showing you the phase, so maybe I'm tricking you, but that's a nice takeaway there. If it's symmetric, then it's real in time. So then there we have our frequency response. We're just laying that over top of that, right? That's what the product is. And so it's attenuating the low frequency. So this is a high pass filter. Okay, so with that, what we're going to go through, this is the design flow for FIR filters that I've laid out in terms of the steps we'll take, and that we'll go through starting with specifications and ending with implementation and verification that we would do. So specifications. So filter specifications. So the common specifications are defining the pass band, right? Where do we want to pass signals? This is a low pass that I'm showing, but it could be a high pass or a band pass. But there's going to be a certain range of frequencies from one end to the other. I'm showing a low pass prototype here, where FP is going to be the frequency defining pass, right? And then within that, there'll be an amount of allowable ripple for that pass band. And similarly, there's a stop band. So we define a stop band out to, and I'm showing it going from 0 to 0.5, 0 to 0.5. So what you're seeing there is common representation of frequencies. It's the normalized frequency, right? Normalized frequency, where you divided the frequency by the sampling rate. So whatever your frequency axis was, if it's in hertz, which is cycles per second, right? And our units of time are seconds. And if we change our units of time to be samples, then it becomes cycles per sample. That's what happens. You divide by the sampling rate, becomes cycles per sample. So the sampling rate itself divided by the sampling rate is 1. So that would be 1 cycle per sample. So it sounds a little confusing, but it's just another way of representing the frequency. Then everything will scale. When we scale the filter, it's very convenient. So you'll see that throughout this presentation. You'll see the frequency axis go from 0 to 0.5, representing 0 representing DC, 0.5 representing FS over 2, half the sampling rate. And that's the first Nyquist zone. And that would be for the case of a real filter where we're showing just one side, right? And more generally, we can have complex filters where we have something that's completely different because it's not complex conjugate symmetric, right? And then we'd have to show something that goes from minus FS over 2 to FS over 2, minus 0.5 to 0.5. And I'll throw out 2 because you'll see it. You'll often see pi in the frequency axis, right? And that's just converting it to radians, right? Radians per second, 2 pi f, radians per second, so hertz. So 2 pi f in this case, 0.5 would be pi, right? Pi radians per sample. And then importantly, all filters will have a transition band. Of this transition band, all realizable filters, right? Realistic filters will have a transition band. That transition band drives the complexity of the filter. You're going to see that. So if you have a very tight transition band, type and frequency corresponds to really long in time. So that means in order for us to do that, we need a very long impulse response. You can kind of see with FIR filters, it's basically a weighted moving average is a simple way to look at it. All right?
So does that mean more coefficients in the long?
That's right. More coefficients, longer duration, longer delay, everything longer, right? And so the idea of a weighting moving average is an easy way to understand filtering. Just an average is a filter, moving average. And that would be an FIR filter where all the coefficients are 1. Right? You're just accumulating all of them over a certain time span, and that's your memory. You're taking the current sample and all the past samples for a certain amount of time and averaging it. Accumulating is just like averaging. You just didn't divide by the number of samples, and that's the pure average, right? So if you look at, for example, if you look at the daily stock prices on the New York Stock Exchange, and it's going like this, and then you look at a 30-day moving average, and it's smoother. And it's shifted, right? So you have the delay and smoothing. It's a low-pass filter. So the other parameter of interest would be the filter order itself. So the order, the number of taps is 1 more than the order. So the number of coefficients, the total number of coefficients would be n, and the filter order is 1 less than that. So if you had 4 coefficients, that would be, right, third order filter. And I'm not mentioning here, but I do want to mention that, so because I'm talking about linear phase filters, the phase is linear. It just keeps increasing as you go up in frequency at a linear rate, just like any delay line would. But if that's just a subset of filters, it's the one we're talking about today. But arbitrary FIR filters can have arbitrary phase responses, and phase is often a very important parameter in the design. So if it's not linear phase, then you have to pay attention to phase. We're so used to seeing magnitude responses and not thinking about phase, but just know in the back of your head that that is a very important design parameter that we can ignore here because I said it's linear phase. And the phase is just straight linear slope as we go over frequency. So the trade space, so this gives us a trade space of, you can take 2 basically. Like you can have the filter order and the passband stopband ripple and trade off the transition width or vice versa. So you can't have all 3. It's one of those things. But this is ultimately the trade space in the design. So we start with those specifications, and then with that, our first step would be to estimate the order. So I'm going to show you some good back-of-the-napkin estimators for starting with, how many taps do you need? You want to get this filter response. You want to meet this specification. How many taps do you need? And these are my favorite ones. My favorite one is Fred Harris. He's my favorite for a lot of things, but his estimate, because it's so simple, right? It says A, the attenuation in dB divided by 22, divided by that delta F. That delta F is that transition band that we talked about, right? And then these other estimators, you can try them out. That's the delta 1 is the passband ripple and the stopband ripple specifications that we had. I'll show you an example of how we do that, but you're converting out of dB to actual magnitude quantity and then popping them in there and getting an estimate. Or the Kaiser window filters. So we're going to talk about the Parks-McClellan and Kaiser window. You'll see that coming up. There's some of the types of filters that we'll design. But those would be the common estimators to use for that. But the one I typically just go to is this. It's close enough. Because what we're going to do is it's just a starting value, and we're going to iterate, right, on doing that. Any questions about that? So this just tells you the Python command you can use that will do this formula, or you can just do the formula. It's simple enough. So here's an example. So with it, let's make this a little bigger. Yeah, so this is a low-pass filter with a passband ripple of plus or minus 0.2 dB, stopband rejection of 33 dB, sampled at 48 kilohertz, so it sounds like an audio low-pass filter. And it's got a passband edge of 9.6 kilohertz and a stopband edge of 12 kilohertz. So we're going to carry that through the different design techniques going forward, and you'll see here how that estimator worked. So the passband ripple, so what you're doing, you're converting dB back to a magnitude quantity. dB back to a magnitude quantity. So it's dB as a magnitude, ratio of magnitudes, it's 20 log of that ratio. Because dB is a ratio of power, is 10 log of that ratio. So if you have the value 0.2 dB, you want to convert it back to dB, we're going to divide it by 20 and then the A log and subtract 1 because it was 1 minus that, and that's 0.023. So that's the example of delta 1. And delta 2 is 0.022, and the passband edge, as in units of normalized frequency, and really we just have to keep the units consistent. We could use other units as long as we keep it consistent throughout. So we're dividing it by 48 kilohertz. So this passband edge right here is 0.2 cycles per sample, and a stopband edge of 0.25. And so if we pass it into these formulas, you can see their use. So the +1 is there because I put everything in terms of total number of taps, where those formulas as derived were based on the filter order. So you're just seeing that difference of 1 again. So watch out for that. And so we plug it in, and you see the example of it getting to be 28.3, and Fred's formula gives you 30. We can use any of them. They're just starting values, so that's their purpose. And you'll see how much they vary in terms of what we use to do that. For this estimator, if you're using it, and if you have a big difference between delta 1 and delta 2, I found it works better to just use the tighter one. So it's just the tighter of the two and square it, and that ends up being the estimate in terms of doing that. So, and you see in the estimator how the delta F is driving the number of taps, like I said, right? So that's your driver. Okay, so now the meat of this presentation is going to be the designing the coefficients. So in terms of the loop that we would do, you design the coefficients, you check the response you get with the tools, you're comparing it to your targets or what you really want, and then you modify the order, you increase and decrease accordingly if you're trying to optimize your efficiency. So this is the four primary methods I've seen, the four most common methods for designing the coefficients. And I'll go through each of those in terms of what's best, what to use, which ones not to use, etc. Starting with this window method. So the window method, this method, it's simple, it's non-optimal. I'll show you why. And it's using typical windows. These are all in Python, they're all in MATLAB, and they're all in Octave as well, in terms of using them for filter design. And there's more info here on doing that. And let's talk about that. So here we'll start with this. This is your in the idea of a filter design, and we often want this approach to get to what we get closest to this mythical brick wall filter, right? The brick wall filter that's not realizable, but there it is in frequency. I'm showing a filter that has, it's going to reject everything above a cutoff. It's going to pass everything without any distortion within its passband. And it has zero phase. So you know what that means when a filter has zero phase? Because we do implement in post-processing zero phase filters. So it's a good takeaway. Anyone know what a zero phase filter is? That's right. It's the same phase shift across different frequency components. And there's something special about it. Something special about it. The zero phase filter has absolutely no delay. Absolutely no delay. So really good, and all this stuff, a really good takeaway is phase. And I said, pay attention to phase. Like even for us, a delay, a fixed delay in time looks like that in frequency for its phase. Okay, you can look at the Fourier transform of a time delay. You'll see that e to the minus j tau omega. You'll see its phase is proportional to frequency. And the best way to see that, the best way, my background's originally RF, so I worked on network analyzers, so maybe this analogy works better for me. But if you take a fixed length of cable, and you picture the sine wave at the input and sine wave at the output, and you compare them, if it's a really low frequency, the phase difference as a time delay between them is going to be very small, right? And then as you keep increasing the frequency, that delay, fixed delay, will be more and more cycles as the frequency goes up. So, of course, we would see exactly that, right? Just see the phase increasing negatively, and that means a fixed delay. So that's what a linear phase filter looks like. That's what they mean when they say linear phase. And the cool takeaway there is that everyone can relate to once they've seen the Fourier series expansion, right? The Fourier series expansion takes some arbitrary waveform, whatever it may be, and you can decompose it into a sum of different individual frequencies, right? So we create a really nice waveform. Perhaps it's for wireless comm or whatever it is, and we want this, no ISI and things like that, and it has all these different frequency components. If we put that through a fixed cable, a lossless cable, that will look like that. At the other end, every one of those frequencies will have gone through the exact same time delay. The phase is different, but the time delay would be the exact same. You're just backing out what I explained earlier. Right? So when you add them all up, you're going to get your original waveform. And you try to do that with something that's nonlinear phase, then you have different frequencies at different time delays. So when you add up all those components, it's going to be a big mess. That's why we need equalizers. This is what a regular wireless channel would look like, in terms of the different delays and all that stuff. So that's why we like these filters, and it's convenient because they're the easiest ones to make. So it's convenient, and we like them. So is that clear? Because that's an important takeaway.
Is the steepness of that phase graph proportionate to the mass?
The steepness of that, it will be, because the steepness of that phase graph is directly proportional to how long we delay. Right? And so you're going to see how the number of taps will relate to this. But it's really,
The duration of the delay is proportional to the slope of it.
That's right. So how far we push in that time delay is how steep that got. If we push even further, it's got to be steeper. Okay, so that's a good thing. So that's why if it was zero phase like this, it's zero delay. And that's what you're seeing. You're seeing in frequency, you see this rectangular pulse in frequency, a brick wall filter. And that's also something just to commit it to memory if you didn't yet, but the Fourier transform relationship between a rectangular pulse in one domain is a sinc function in the other domain. And you just see it so many times, so many places. It's one that, if I stop you on the street somewhere and ask you, you'll know like that. So that's what we see on the right. We see the sinc function as the impulse response. Yep.
Is the reason that the sink is able to achieve zero phase that the sink is non-causal?
Yes.
Okay.
Absolutely. A good point. It's completely non-causal right now. So we can't realize without, we do it in post-processing, we can implement zero-phase filters in post-processing, and we have a result that lines up on both sides, right? That's the benefit of it. But we can't do it in actual implementation because it's completely non-causal. So you're seeing the impulse response for a non-causal filter as a sinc function that has to go to plus or minus infinity. It's not only non-causal, it has to go for all time that was and all time that will be. And if you can do that, then you can make a brick wall filter, right? But we can't do that. We can't do that. So first step is we delay it because of Mr. Causal Police in the back there says we can't do it. So we delay it to make him happy. And that's what we kind of get the impulse response to the right. And then we have to truncate it, right? And then we're completely causal. Completely causal. A filter that is completely symmetric will be linear phase, an FIR filter. So if it's completely symmetric, it'll be linear phase. So we're going to truncate it symmetrically so it's still balanced that way. Okay, so that's just making it, that's saying, hey, we want this ideally. This is what we got to do. The longer you delay, the better we can get. So doesn't that make sense? When we just talked about, hey, if we want a really tight filter, we need a really long time delay. Well, you can kind of see it. It allows us to include more of those important tails that define that brick wall response that we're trying to get to. Make sense? And thanks for the questions, by the way. It helps. Keeps me where you guys are. Otherwise, I'll talk too fast. So if you want me to talk fast, don't ask questions. So the rectangular window, that's what you saw where it's called a rectangular window. We just decide to truncate. That's it. We multiplied it in time with a rectangle. So we're going to see lots of these rectangle pulses and lots of sinc functions, right? You see that coming up again and again. So by doing that, that's what happened to our frequency response. See, we're getting passband ripple and stop band ripple because of that very thing. Let's see why. So this is detailing why. If you follow along with me, we started with our desired frequency response as the rectangular pulse and frequency, right? And the inverse Fourier transform of that is a sinc function. And we delayed it in time to make it causal once we get rid of that tail and combined with multiplying it by a rectangular window. So those two things made it causal and kept it symmetric for our linear phase filter, right? And that resulted in the realized frequency response. We wanted this, we got that. And just to understand that, the main takeaways here give you some more transform review, right, in terms of that. So the top one's your Fourier transform. This is your continuous time, continuous in frequency. We just have a sinc function in time, and we have a sinc function in frequency, and it's a rectangular pulse in time. And it works either way. But the main thing is that is also good to keep in memory because it shows up a lot. If this has a duration t, right? If the width of that is t, the first nulls of that sinc will be at 1 over t. Okay? The same thing, if you swap time and frequency, you'll see the same result. So if it has a width t, the null, where it hits the null the first time, is 1 over t, and then the other nulls are multiples of it. Okay, but that's going to help us see some stuff here. If you keep that in mind, the null's at 1 over t. Now, the discrete time Fourier transform. Don't get confused with the FFT and the DFT. This is the discrete time Fourier transform. It is sampling what we started with in time here all the way to infinity. So there's an infinite number of samples. Okay, and we'll have n samples where it is 1 but the samples keep going. That's what makes it the discrete time Fourier transform. The discrete time Fourier transform will be continuous in frequency. So when we get back to the filters and we talk about the frequency response of the filter, where we're just saying, hey, it's a low pass. When you look at frequency responses, whether it's a digital or analog filter, they're continuous in frequency, right? You're looking at the frequency response. You can sample any frequency, any signal at any rate continuously. I could have a 1 hertz or a 1.001 hertz is still at that sampling rate. So there you have continuity in the frequency domain in terms of the frequency response. So with that, we use the DTFT, which just means add all these zeros and you'll get this result. You get something that's continuous in frequency. We'll see some examples of that. But notice, same thing. It's the exact same thing. What you had in whether it was continuous time or discrete time, you're getting the same result. But what else do you get? You get this periodicity in frequency. It becomes periodic. So if you've seen A to D and D to A conversions and aliasing and stuff like that, then this would make sense to you. If not, then this is your first intro to that. And when you see A to D and D to A's, you'll see that periodicity. Sampling in one domain makes it periodic in the other domain. Sampling in one domain makes it periodic in the other domain. And it'd be periodic. It'll keep the spectrum, what you have here, will keep repeating at every multiple of the sampling rate. Okay, so that's why you'll see it. If you've seen an FFT, you see it goes out to half the sampling rate and you keep going. And if it was a real waveform in time, it repeats again exactly. And then if you kept going, it would be mathematically equivalent to it being completely periodic. You'd get the same result. Is that clear? So that's what happened. All we did was sample it. We got this periodicity, and I'm just showing you from 0 to Fs. Why? Because if we kept going, you'd just see the same thing again and again and again. Right? And then the point that it's still n samples. We still have the null at 1 over n, and it's going to infinity. So finally, we have the discrete Fourier transform, which the FFT is an efficient algorithm to give us. Like the exact result. But it's the discrete Fourier transform. The only difference is it's a finite number of samples in time and in frequency. We have n samples, that's it. We're not extending it out. And so we just get n samples in frequency. And now it becomes discrete in frequency. It's discrete in frequency. So we had something that was continuous in frequency as long as we kept going in the time domain. Here we stop in the time domain, it becomes discrete. So you have the discrete samples. That's a big thing to keep in mind, because that's where you're going to see that thing I said was a rookie mistake in terms of the filter design comes from this. You think, oh, it's all zeros. It's great. It's perfect. It's 1. It's all zeros. I'm going to define that to be my frequency response. What you're not realizing is this is the frequency response, and see the ripples that are there? They're here as well, because if you take this and look at the frequency response of that, it will reveal those ripples that are in between. You're only seeing part of it. I'm seeing part of it because it's discrete. Because it is discrete in frequency, yet your filter has to work on continuity in frequency, right? You can have any possible frequency at the input and output of your filter, not just these discrete particular samples. If you were working on a system where, hey, I'm only going to have tones at these particular frequencies, then using the DFT could be a good approach. And we'll see that. Any questions about the transform review? The minimum that you need to know to see what I'm going to tell you next. And what I really want you to see is in all cases, it's 1 over n. And I didn't say this clearly enough, though. The DFT is giving you samples on the DTFT. So you're getting samples on it. If you add zeros here, which is pretty neat, you can try that with an FFT. If you zero pad it, you'll get more samples in frequency because it has n samples in time, n samples in frequency. You know where those samples will be? Those samples will be right on this dashed line. So it's a perfect interpolation of that ultimate continuous DTFT that you want. So that's how you can plot the DTFT. Just zero pad the heck out of it, and you'll get something that looks like this, at least for your plot. So all good takeaways that'll tie in back to this FIR filter that we're supposed to be talking about. So we had this rectangular window, right? We had this rectangular window, and what did we see? So now you can see what happened behind the scenes, how it got smeared. So the top one says we had this impulse response, right? Our perfect impulse response, which we can predict. We know we want a rectangular function in frequency. We know that's a sink. Very easy to compute every sample on a sink. So we can get the exact values of this impulse response. We want to go out to infinity. Now, we can get as far as we want in terms of our processor having the resources to compute it, right? And so then we multiplied it by a window. We multiplied it by a window and made it causal and realizable. So it's multiplying in the time domain is convolution in the frequency domain. And it goes vice versa. Multiplying in the frequency domain is convolution in time. We covered that. So multiplying in the time domain is convolution in the frequency domain. Okay, so that means this window, so you're seeing a lot of different rectangular pulses and sinks everywhere. You got to keep track of them, right? Oops. I have a blank button. That way, all right, I'm trying to explain something. It may not. This rectangular function of n samples has a sink with that first null at 1 over n frequency, right? This is a different rectangular function that has a different sink. So there's two sinks going on here, right? But ultimately what I want you to see is, okay, there's this desired frequency response that we want. We multiplied it in time. We multiplied it in time by a rectangular window. So we're going to convolve that desired one with this impulse response. With this sink function that we get in frequency, right? We're convolving the two. And that is giving us this realized frequency response. We slid one past, convolved and smeared, if you can picture that. But notice the 1 over n. The 1 over n is what ends up being our transition band. So that's the driver of the number of coefficients. If we had n samples, as you saw on the last slide, to give us a first null at 1 over n, then that is what this transition band is. So you solve that, n equals 1 over delta. So that's your driver to the number of coefficients that you need, that transition band. Make sense? So there you see in every one of those estimators, there is a 1 over delta at in terms of that 1 over the reciprocal of the transition band was driving the number of taps, so it's directly proportional to that. So try not to design a super low pass filter that's way oversampled with such a tight transition band when you can downsample first, and it really makes a big impact into how many coefficients you need. You can picture that, right? You're changing the transition band. That's a ratio of the sampling rate. So you want to make that as big as you can, so you should sample as low as you can. Okay, so with that, what we can do, we saw the response we got. We can use an alternate window instead of the rectangular window. So you saw the result of a rectangular window. It created a sink, and a sink has lots of ripples in terms of doing that. And so if we multiply it with more exotic window that tapers slowly, then we get much significantly reduced stop band, but we'll always get this wider transition band that results. That's going to be your trait. Okay, so it's going to, by doing that, instead of using this rectangular window, you slowly taper it, and these will go significantly lower. Your stop band will go significantly lower, but you're going to come at the cost of increasing that transition band. And that's often a good trade to make. It's often a good trade. I'll show you why. This is comparing the blue. The dashed blue is the rectangular window. It's called the Dirichlet kernel, which is the Fourier transform of a rectangular window. It's called the Dirichlet kernel. So now I know a fancy word and show off with, but that's what that is. It's the Dirichlet kernel is in blue. Notice it just doesn't go away, right? It's like that relative that stays for 2 weeks or something. It just won't go away as you go so far, and it's only going down 1 over f, right, as you go away. So it's a very slow roll off. And you can see the effect of these by simply, you're seeing the DTFT, right? The DTFT. How do you get the DTFT? Zero pad the Fourier transform. So take any of these windows, and we can play with it in Python later. You'll see it. Pass it in, take the FFT, but not just the FFT. Zero pad the heck out of it, and then you'll see this result. And it's telling you everything you need to know. Pretty cool. So you can compare all the windows you want to use, and you can see what the trade is in terms of window. You're trading your main lobe width, which is going to be your frequency resolution, how much you can really resolve a frequency, versus how far these side lobes are down, which is your dynamic range, right? The picture trying to work with two signals, one really strong, one weak next to it. It'll be totally buried by this. You know, it wouldn't even have to be next to it. It could be way out here, two signals, one there and one there. And if we processed it with this rectangular window, the other signal would be completely buried. You picture that? And this one allows us to, because this is what will convolve with your spectrum, right? So you'll convolve it with your spectrum. You had a perfect spectrum here, you would see this very shape as an impulse, right? And if you had another impulse here representing another frequency, then this whole shape will appear there as well. And a picture how one would get buried by the other. And this Kaiser window is one of my favorite windows for filter design, because it's one of the ones that has a little knob, beta knobs. That's what I adjusted here. Beta is 8, beta is 12. You can go down to beta is 0, is a rectangular window. So it's like all the windows all in one box. In terms of that. Any questions on what you're seeing? Just a discrete time Fourier transform of the window itself. It's going back to what I was showing right here. What is this that's going to convolve with that to give you this result? You kind of picture how like, oh, all these high ripples are giving all this. So in this case, we're going to make some awesome filters by involving it with something that's, 125 dB down. Or you want 200 dB down, we could do it. So it's whatever you want. So window summary. So this was our first one. It's you establish the desired frequency response. That's the step you take. What kind of frequency response do you want? It can be any response. What do you want, right? And from that, if you can get the impulse response for that, which is the inverse Fourier transform, not the inverse FFT specifically, but the inverse Fourier transform. So in our case of the Rickwall filter, it was a sink. That was easy for us. We know, okay, that's easy. We know a rectangular function, one domain is a sink function to the other. We have our impulse response. It's the impulse response that you would have in the perfect continuous time system. That's what you're looking for. If you can get that, then you're on your way to windowing. Then you just take that, truncate and window, you're done, and you can pick the results based on what you saw with the types of windows that we have. This is also, it's a very good go-to filter design approach when you have minimum resources, because it takes minimum resources to compute your coefficients or recompute them. So if you have an application where you want to dynamically change the filter, then this is a great one to do versus some of the other methods I'm going to show you. But the other methods I'm showing you are saying you have a computer there, you're designing your filter, and you just want the coefficients, and you're going to put it into a device. Then we're not worried about that, and you use those other approaches. Unless, of course, we get into with my favorite approach that you can see later, if we get into a point where it doesn't converge for whatever reason, then I fall back to this. And I fall back to the Kaiser window specifically. I'm getting very close results. So frequency sampling, here's our next one. So frequency sampling, this one is very simple. This is the one that you would see somebody as soon as they learn about the Fourier transform and as soon as they learn that the coefficients of the filter is the inverse Fourier transform of the frequency response, that you would use this approach, and it's using the inverse DFT. That's the inverse FFT specifically. It's using the inverse FFT in contrast to the inverse Fourier transform. See the difference? Inverse Fourier transform is your frequency response as a continuous function. Inverse Fourier transform as a continuous function. What does that impulse response look like as a continuous function? Sample that in window. That's windowing. With this one, we're going to say, hey, here's the frequency response we want. We're going to sample that and put that into our FFT, saying these are the FFT samples. Inverse FFT of that, that's frequency sampling. Do you see the difference? You see the difference? And this is putting some actual quantity on it in terms of how much difference does it make. So what you're seeing is the comparative response. This is the impulse response you would get, and this is in dB. You should look at your impulse responses in dB to see the actual distortion levels they're talking about. If I looked at that as a magnitude, you didn't see any of the stuff. But you're seeing in orange or red here, that's the sync function. This is a pure sync function in terms of the magnitude of it converted to dB, and it's truncated. It keeps going like this, right? So our error in that case, using that one as the filter, is the truncation error. And I showed you all about what that is. If I take this desired frequency response, and there's 100 samples here, right? Or 101 samples. So what did that mean? I filled this with, and the FFT is periodic. So the 0.5 to 1 would be a mirror image of what you saw from 0 to 0.5. Okay, that little detail we introduced earlier. So if you take those samples that you want, you take 101, sample it, and then you take the inverse FFT of that, the impulse response looks like this, the blue. Anyone know what that's called? What we would call that? The error that we're seeing, why is the blue higher than the orange? So it's called officially, and it is, time domain alias. Okay, so if you've been exposed to A to D, D to A conversion, you have aliasing and anti-aliasing. It's the same thing. That happens in frequency. This is happening in time. And a way to picture it is, okay, I told you about our perfect sync going down, and it keeps going down, right? So what's going on beyond here? What's going on beyond there? If there's aliasing, it's folding back. And you see it. So this energy that's just beyond there folded back and raised it up, and that's why that's higher. So this error is due to that aliasing. It's kind of a So you often hear that as to why don't you want to zero a bin in the FFT to get rid of the frequency, right? Why is that bad? Why is zeroing bins bad? It's the same thing. It's this frequency sampling. It creates time domain alias. And the effect of that blue versus the truncation that we have in both cases is worse. It's worse to add the blue than to just take that truncation in terms of doing that. Any question on that? So this is showing the effect in terms of if you were to do that. And why I say it's not recommended, because we can compute the coefficients just as easily other ways. And given that number of coefficients, we're going to get a better result. Right? We want the best result we can get for the resources we're using. So this tells you the difference. So again, if I use those, this is just all I did to keep it apples to apples, is take the frequency response of those coefficients that I showed you. All right, so this these coefficients, the actual coefficients, not the dB log magnitude of it, but the actual coefficients, the sinc function in one case, or the inverse FFT. If I take those 101 coefficients and I look at the frequency responses, the filter, that's what we see. This is the frequency response where there's the pass band, there's the stop band, and see the stop band is significantly worse in the case when we use the inverse of the FFT. Make sense? Anyone have any questions about that? Because this is a real important point. If there's any confusion before I move ahead. Can you make that trade? Yeah, so in the other approaches, would you balance that? You can define what we want to trade with that. But this is just saying, here's the result they end up getting in terms of what we didn't do. In both those cases, we could have further windowed them and got much more improvement here. I kept it apples to apples. So we can, either one of these approaches, we can then go and now let's window it so we don't have as much truncation in both cases. We can do that. But you still have this error that you introduced and you're still worse overall when you compare the two. So this was a nice comparison of that directly. So it's zooming in on the pass band, we see the bigger error. Zooming in on the stop band, and we see the bigger error. So that's the takeaway of frequency sampling. So where frequency sampling is good is it's going to be exact at the frequencies that we sample. So remember, this came from sampling frequencies, sampling the target frequency response, sample that, take the inverse FFT. At those samples and frequency, the frequency response will be exact. There'll be no error. So if you had a particular system where, like OFDM, for example, where you're working on very specific frequencies, then it's a very good approach. Right? But if we care about what's going on in between the frequencies, like a generalized FIR filter that we're trying to design, then this isn't a good approach. So I'll say it now because I'll show in the notebook. And where this technique, what's close to this technique that is very effective, is to oversample the frequency domain. Okay? If we oversample the frequency domain, like put in not just 100 samples, put in 10,000 samples. Okay? Take the inverse FFT of that. And why I distinguish that from this frequency sampling approach, because what we're doing with that technique is determining the best estimate of impulse response that we want. Remember, the windowing method is get yourself an impulse response as a continuous time domain impulse response. Well, if you put in 1,000 samples here, you're going to have 1,000 samples here. You'll have 1,000 samples in time. So you're stretching time way out. So what you're doing is you're moving this corner where it would fold in on itself way, way out, further and further. You can picture that? So you're minimizing the time domain aliasing. At some point, you're down below the don't care point. And what you did is you got yourself an impulse response because you didn't, in this case, you get your impulse response because it's a sink. We know it's a sink. Just use the formula, get the samples of the sink. But what if this was some arbitrary shape? And I'll show you that in the notebook. What if we're doing some weird, wild shape and you want to match a filter to have this arbitrary phase and magnitude? And this is a great approach for that because it's your fast path to getting the impulse response. Just oversample it to minimize the time domain aliasing. Kind of the exact same thing as if you are familiar with ADD conversions, sample it really high to minimize the above the bandwidth, right? To minimize the frequency domain aliasing. It's the same thing. So you'll see that demonstrated. It's a great approach because it's quick and easy, and if you want to get frequency responses that look like the shape of butterflies, you'll be able to do that, right? Just do anything arbitrary, and it's a matter of having a lot more samples, whereas this approach, and then calling frequency sampling, says you want an N-tap filter, then you have N coefficients in frequency, right? N samples in frequency. You took the inverse FFT and narrowed your coefficients. That's frequency sampling. Not what I just described where you oversample it, and then we can truncate and window just as we do with the windowing method. That would be, see the difference? Okay, so now, how are we doing? Equiripple and least square. So these two approaches are the optimum filter design approaches, right? That would be the, in fact, I'll tell you right now, the least squares is my go-to. When I need a filter, I go to least squares, and especially for wireless comm, where we're interested in like RMS error, things like EVM, not peak error, right? So that's the difference between these two. But let's talk about them. They're both useful, and all the tools to do this quickly are in MATLAB, Octave, and Python. They're at your fingertips. So Equiripple, this is the Parks-McClellan, uses the Remez exchange algorithm, and it's best. It's the best filter you can get from a target response that you want in the min-max sense. So it has the lowest peak error. Okay. And in contrast, least squares is best in an RMS error sense, least squared error sense. Minimize the least squared error. So the least squares approach, it has greater excursions than the Parks-McClellan, but it's only at isolated points. So overall, it's going to be much better, right? So if you're looking at EVM of a waveform, of a QAM waveform or something like that that's filtered with this, your EVM will be much lower than if it was filtered with Parks-McClellan, where that passband ripple degrades EVM, for example, for wireless comm folks that got exposed to that. Any questions about that top view? So the design tools in Python, it's the signal library, what we'll be pulling up and using, SciPy signal library, and it's called Remez. For Equiripple, same thing in Octave called Remez. It used to be called that in MATLAB, I believe, 30 years ago maybe, but it's called FIR PM for Parks-McClellan. And then least squares that are all called FIR LS. Now, MATLAB and Octave are pretty much a clone of each other, so what you learn in one is the same as the other. Python, it's not, but at least the name is the same. You can help on each to use it properly. But this is showing specifically how you would create your filter in Python for doing least squares or Parks-McClellan. So the top line here is defining the bands. So the bands is DC to the stop band edge, to the pass band edge, to the stop band edge, to Nyquist. And the 2 is in there just because of the default it's using for what it's defining as the Nyquist frequency. Nyquist being half the sampling rate. So what I was showing is 0.5. They're calling 1 in the tool, so it doubled it. So you just have to be careful of that. In terms of what are they calling it. You can also pass in what you want to be your exact frequency if you want to work in your units as well. And then Remez, it's doing, so that why that wasn't consistent would be nice, but it was 1 for LS and 0.5 for Remez, so that's where the factor of 2 is for the least squares versus the Remez. Does that make sense? That we're just defining what we want to be passband edges, and then we define what the targets are, and that's this second parameter here, 1, 1, 0, 0. So pass, stop, stop for least squares. But for Remez, it's not 2 groups like that. It's just 1 group for each band. So it's pass and stop. Pretty clear? And yes, it'd be nice if the 2 functions were the same, but they're not. Yeah. So this would be in units of normalized to this unit that you have. So right here, this is half the sampling rate, 0.5. Let's work on the Remez one because it's direct. They're using these units directly. So if I wanted to pass everything from 0 to 0.1 in these units, right? And then I wanted to stop at 0.15. Now I'm defining my delta F to be 0.05. All in units of cycle per second. So here's back to that filter that we were talking about, right? Where we said hey, we want to do a 9.6 kilohertz pass band. And that's saying where we want to pass before it leaves this ripple spec, right? So it's very tight. It's not a 3 dB edge or anything like that. And then same thing with the stop. Where do we want to stop? So you're seeing here least squares versus equal ripple for the same number of taps, right? And so this is what I'm talking about. If we zoom in, we can see, we can yell at it right here. Tisk, tisk, you went off on my boundary in that one little spot, but it's so much lower everywhere else. And it's not getting credit for that, right? So that's least squares versus Parks-McClellan is going to be perfect in this min-max sense. So that's something to be proud of too, right? But it's not what we always need. That's something to pay attention to in all specs, by the way, too. Sometimes we constrain ourselves to be max, thou shall not cross this. And the algorithm and type to get there could be much better if you said, hey, what do we really want in this particular application? That particular application is better with RMS error because we're averaging over a packet or whatever we're doing anyway, much better. It's details like this that we sometimes box ourselves in by saying, oh, not cross this line. So that's showing it. So then you got the 12 kilohertz stop band, sampling rate 48 kilohertz. So you're just dividing these by the sampling rate to get to normalized bandwidth. And so that's what I'm passing in for both cases. Does that help you? The LS band is double because the half point was 1. Oh, you're right. That is an error. That is an error. It should be 24. Thank you. Yep. That's right. Because on previous. Yeah. Right. Is that clear to everybody? And you'll see when you look at a tool and look at how you pass in your own FS directly, and then you don't have to normalize or all that type of stuff. But working in normalized frequency is very helpful for other reasons anyway. So get used to it if you don't, and it may benefit you later. But that's a good comparison because it's the exact same number of taps of what you're getting. And there are, that we're not going to talk about, but there are some uses of FIR filters like in multi-rate processing where you're changing the sampling rate, going to lower rates, where you get this aliasing of all this stuff that's coming out here, right? And the fact that this is going down and keeps going down is really good for those considerations too. When you have something here where each one of these is folding in and it starts accumulating up, this is good for that as well. So if you are doing any like polyphase filter implementation, for example, or resampling, and you're designing the coefficients for that, don't use Parks-McClellan, use least squares. But it's my go-to, use least squares. Number of the passband effect on the number of taps? Yeah, so there's no the number of taps affects the transition band, but ultimately what you're getting is, you saw with the rectangular filter how it has 1 over n, right? That can be your lowest low pass filter, right? 1 over n, it's the reciprocal of the length and time. And that comes up everywhere. Your frequency accuracy is the reciprocal of your length and time, your observation and time, your ability to resolve frequencies, right? So that affects the number of taps. It's how tight it can be. And then when we start windowing, now it's no longer 1 over n, but it's like maybe 1.5 or 2 times that. But that's the trade you want to make because of the way we can attenuate the stop band. Make your filters twice as long, and then window, and you get a great filter, right? But does that make sense? Yeah, ultimately, when you're concerned about how tight can we resolve in frequency, can't get away from it being how long are you observing. And if you're observing something, is it stationary for that long time to be able to just keep up with that? So all those things come into play when you start getting into this. So there's a summary all in one place of the different design methods we saw. And I come back to when I said, least squares is the one I will go to. And sometimes I'll get into some weird condition where it won't converge. And it's obviously it's not converging and then I fall back to the Kaiser. And this is what I'm talking about. It just comes so close to the optimum least squares, right, in terms of its performance, as far as a good window filter to use. Least squares is optimum in the least squared sense. You can't get better when you talk about your least error from a target sample by sample, right? So it's the best you can do. And the Kaiser window is coming pretty close to that. And you know, to the extent you care about that difference, it's good enough, right, in terms of that. And I love this because I teach courses on DSP and signal processing. It used to be, before COVID, it looked just like this. It would be in a hotel conference room near where I live. We get to see everybody. And then I went online with COVID and no one would turn on their camera. This guy's in my class now. He turns on his cameras. But yeah, that's where I went. That's why it's all recorded, because I couldn't talk for 3 hours. And then once I recorded it, like, how am I ever going to do this live? Like, I would do 50 takes for every 3 minutes. I just couldn't. Very different. But this is great because this is good memories. All right. And so implementation. So with that, this is, you know, the implementation detail, a lot more details. This is coming up next month. If you are interested, you can jump in. It's actually in a few weeks through the Boston section IEEE. So you can find that there, where it's a lot more than just filters, but this is part of that course in a lot more detail. And then also these other courses through DSP related. So these are my 3 primary courses: DSP software, radio, Python applications, and then DSP for wireless comm. And they're offered through both of those avenues routinely. So the IEEE and DSP related. And it's a lot of fun, right? Yeah. Okay. I had them come to tell everybody. And now for the Python tools. So what we're going to use with the Python tools, and I'll fire it up. And you're welcome to, if you installed Miniconda or Anaconda, and if you install mostly the environment that I have, you'll be good to go now or later. But we're going to use SciPy, Matplotlib for plotting, and NumPy basically for the filter implementations. And so you asked about Anaconda, and I had you install Miniconda. So both work. So Anaconda gives you everything. And then you learn once you're developing in Python that it's good practice to work in environments, right? And that, you know, it's an open source community. So this tool and that tool would be compliant and matched as soon as you try to upload or something else. Anaconda, you gotta match to everything. And then if you're going to make separate environments, why are you just going to keep plugging everything over? So the idea, the best practices I found is work in environments. And every single project you do, it's easy. The Conda is a great environment and package manager in terms of doing that. And it's been accelerated by its combination with Mamba in terms of that. So it has no issues it used to, but it's handling that so easily that once you get through the habit of doing it, it's just easy to have a new project, new environment. And that way, if you're working with other people, you just hand them the stuff and just handing them the minimum your requirements file, the minimum amount of tools that you need. And then if you upload something later to it, it's not going to break so easily with the 50,000 other things that are in there. So that's why I like that. That's why I did the setup guide that way. And in the setup guide, it has you create an environment. So that's good practice. So I have an environment for every single project that I do. I'm done with the project. It lives there. I can come back to it in 2 years. And it's still going to work. Right? So which direction I went with other things. So that was the thinking behind that. Here's some references. Oh, this is fun. If you want an even easier, so this guy that Robert Farinack, he wanted me to demo this Knox filter on YouTube, and he talked to me first, and I gave him, I started talking like I'm talking to you people, and he's like, wait, whoa. And so he trained me in how to explain this to like a high school student. Worked out great, I think, in terms of real simple explanation. So if you want an even simpler explanation of filters, that's good. But it was a fun demo where I originally, why I did it, because I had this idea of doing Tone Petty. Do you guys know who Tom Petty is? Canadian. That's right. So my Tone Petty demo, I have Tone Petty. I have this picture I made of him with a kilohertz tone behind him, and he's frowning. I did all the Photoshop stuff. He's upset, and so I can take Tone Petty and I pass it into this microchip part and the SAMI 51 processor, and out comes Tom Petty. So it's a notch filter. So it's a neat demo of a notch filter, and it converts Tom Petty to Tone Petty. But I can't put that on YouTube, so it's now some African sunrise music or something that I found that was free rights music demoed. But yeah, that's a lot of fun. You can find that